In this lecture, we're going to start to bring back some of the ideas we've been talking about in the last couple of lectures back to spectroscopy as we gear up to look at NMR spectroscopy in a lot more detail. So what I want to remind us about is that we wanted to look at some ideas related to absorption spectroscopy. Well, absorption spectroscopy requires an absorption event. Okay, so the key thing to kind of grasp before we get into this in a lot of detail is that matter can interact with light to become excited. And excited is actually a technical term. We'll talk about excited states. Now, this interaction is called absorption. I was very careful in my use of the words here because spectroscopy involves the study of how light interacts with matter. Okay, so we want light to interact with matter, and what are we actually wanting to happen from that interaction? We want matter to become excited, and that for it to become excited, that energy must be absorbed. Okay, so let's take matter. Now this matter is going to look a lot like those photons, but it's because my artistic prowess is limited. I'm going to take matter and I'm going to interact it with some energy. Matter, energy. Okay, so what I want to kind of emphasize here is that the energy could be from light or from light particles, which we consider as photons more precisely. Now, if things are just right, that energy can be absorbed. And we can actually write this as a bit of a chemical reaction because we're transforming matter. It's just not necessarily breaking and making bonds like we would think. We can, we'll see it. But anyway, the matter is transformed at first into an excited state. Let's say that this person, this matter, it's not a person, is excited now. Okay, so the matter took on the energy to enter an excited state. Now, there's a bit of an issue with this chemical reaction. It's not necessarily, it doesn't look to be balanced. It is, but it doesn't look to be. That is, in organic chemistry 1, I harped on we cannot create or destroy energy. We can only kind of transfer it from different states. Okay, so what's happening here is energy is being transferred. Now we transfer that energy in the form of potential energy. That is, if you recall, if we have some sort of floor and we put our matter, and I'm going to give the matter just a little bit more emotion. Okay, beautiful. So the matter is like a bowling ball that's on the floor. There's a shelf up here. That shelf is high, it looks scary. Matter is not too excited about it, but it's happy, it's content, it's on the floor. But then we introduce some energy in the form of some photons, and that energy allows that ball to get lifted up. Maybe photons is a bad metaphor. Let's imagine that I'm the photon. I grab the ball, the matter, and put it up on the shelf. Okay, so if the energy is just right, the energy is absorbed. And the state of the matter has changed. Its position has changed such that it has increased potential energy, and it's now we call it excited. It's probably nervous, but nerves do cause, you know, some. It's not excitement like euphoria or whatever. But anyway, whatever. Let's not get into emotions. Okay, so the floor is no longer the state where the matter is at. The matter is now at a higher energy state. And that higher energy is reflected into an increase in potential energy for this particular system. This is just to show that we're not destroying the energy. The energy is being taken on, it's transferred into the matter, and the matter is now excited or in a higher energy state. Okay, let's introduce some terms related to this. So the starting state is called the ground state. It's not hard to see why I chose this picture then, just flipping back. Matter starts on the floor or on the ground. So we're in the ground state. This is the starting state of matter prior to absorption. Okay, so we have the ground state, and that's in contrast to the excited state. Okay, the excited state is the higher energy state, and that energy can be reflected in a number of ways. I chose potential energy as the past example. We can have increased thermal energy. We can introduce, if you think about it, we can introduce radiation or photons to a system to increase its average kinetic energy or its temperature. We can heat things up using photons, right? We can heat things up using light. I mean, it's a big problem what's happening in the planet right now. Okay, so anyway, we'll talk about that later. Okay, so the excited state is in contrast to the ground state. This is the higher energy state that results after the absorption event. Okay, so I want to be able to use these terms in upcoming lectures, so please be aware of them. Excited, higher energy, results after absorption. Now, what's interesting about this interaction of light with matter is, and this is super awkward, is that the energy must be a perfect match. Okay, so this is where we're going to get into some quantum mechanics a little bit. Not the math, but just those odd concepts that at first don't seem super intuitive. But remember, we're working with things that really aren't intuitive. Small molecules at atomic level, photons, particles that are massless yet move at the speed of light and are both a wave and a particle. Okay, anyway, I'm just saying intuition's out the window a little bit. We have to accept some of this stuff or go do the measurements ourselves. So we have resonant absorption, which is related to this point that I just mentioned. Okay, resonant absorption says that the energy that is absorbed must exactly match the potential energy. I'm not going to include potential. I'm just going to say the energy difference between the ground and excited states. Okay, so this is hugely important, and it's related to everything must be a perfect match. And this is, again, a little bit of quantum mechanics. Okay, now what I'm saying is, if we go back to our example of the ball or the matter on the floor that was content, and we let energy get absorbed into that matter, transferred into that matter so that it can reach up to the shelf and be in a higher potential energy system. Let's say we quantify that difference in energy between those two states. In the example, I chose the floor as one state and the shelf as another, right? The floor is the ground state, The shelf is the excited state. And the difference in energy was reflected by an increase in potential energy when we went from the higher, going higher up in gravity interacting, and that introduced our higher energy system. So this is just for us to visualize. Now, where this gets to be counterintuitive is, let's say that for whatever that matter was, the energy required to get from the ground state to the excited state, the energy that I would expend if I lifted that up, is exactly 5 calories. 5 calories. Now, what's interesting about this is at the atomic level, for resonant absorption to occur, for a photon to interact with matter, where it's no longer me picking up the ball, but it's a photon, okay? That photon must have the energy equivalent of 5 calories. That's like me going out and I'm looking at my watch and I'm saying, okay, this is going to take 5 calories, my fitness watch, whatever, that tracks calories. This is going to take exactly 5 calories of energy for me. I'm going to have to burn exactly 5 calories to lift that ball and put it up on the shelf. Now, what that means is if I give the situation 2 calories, that is, I only expend 2 calories of energetic effort, the ball's not going to get up on the shelf. That should make sense, right? If you have some sort of physical task in front of you and you don't put forth all of the effort required to do it, it's not going to happen, right? So I lift the ball maybe part way up, okay, with only 2 calories expended. But where this gets counterintuitive is that it has to be exactly 5 calories of energy expended to get the ball into the excited state, okay? Now that doesn't make sense at like a big human level, because if I walk into a room and I want to put the ball on the shelf, okay, and I say, you know what, I'm going to like do some jumping jacks, I'm going to sweat, I'm going to crack my knuckles, I'm going to get really pumped up, blood flowing, and I'm just going to lift that thing and put it up really quick. It's going to cost 15 calories, but you know, who cares? I didn't get my steps in today because I was recording lectures. The thing is, at the atomic level, while I could do that and expend 15 calories and accomplish the same task, for resonant absorption to occur between a photon and a piece of matter, okay, the energy supplied must exactly be equivalent to the difference in energy between the ground and excited states. So if expending 2 calories doesn't work, it turns out that expending 7 or 15 or 200, way more than you need, is not going to work either. The transfer of energy must be perfect and must perfectly reflect the gap in energy from the ground state to the excited state. And again, that's some quantum mechanics are buried in there that we could show all of this if we had time. So that's a really important concept to hold on to. That is, higher energy, supplying higher energy will not lead to absorption. Supplying more energy than you need will not lead to absorption, okay? Supplying more photons of the perfect energy will lead to more likely absorption events to occur, but that's more of a probabilistic event, more of like you increase your chances of absorption occurring, as opposed to just higher energy does not, you know, necessarily mean more photons. It means a higher frequency or shorter wavelength. Okay, so let's get some of this onto our notes. So in spectroscopy, we use, or we control, the energy of light sources to supply specific energies. And often this is done with lasers. That is to say, we know what photons go in. And that's critically important because they got to be just right for absorption to occur. So light is our source of energy. And that light is used to promote ground state to excited state. And that process of moving something from the ground state to the excited state is called excitation. So what we do is we do an experiment where we have, and typically people call this our matter. Instead of putting the smiley face, that doesn't really bode too well in scientific journals. We have A. A is our matter. And we're going to add to that light a photon with a particular energy. Now, E is a little bit vague, so we're going to use H nu so people know that we're using light as the source of energy. So this is sort of our symbol for light energy. And what we do in a typical spectroscopy experiment, because we're studying, we don't know yet. We're trying to do an experiment and learn some things. But what we typically do is we say, okay, let's try this energy of photons, and we plug it into the system, and nothing happens because this is a Goldilocks scenario. That energy has to be just right for absorption to occur to get us to an excited state. So we try photon A, nothing happens. Photon B, nothing happens. Photon C, nothing happens. Photon D, something happens. That is, we have the appropriate energy. And when we do that, when we have just the right energy, just right, Goldilocks, we get resonant absorption. We get resonant absorption and excitation occurs, and our matter becomes excited. Now, what does that mean for our matter? Well, we're just going to redraw our matter. Okay, we haven't transformed it. We haven't, in many cases, especially in spectroscopy, we haven't necessarily transformed the matter into something that looks completely different. Like we haven't made like dirt into gold or something like that. Okay, rather we've taken that matter and we've pushed it up onto the shelf. We've taken it and put it on to the excited state. So we put a star next to it. That is, the star is the equivalent of the face that had like the jaggedy lines and all that stuff to imply that it was a higher energy state. So this is excited now. Okay, well, I said what we do is we shine one photon, A, B, C, D. Oh, D was perfect, great. Well, that's a little impractical because, I mean, we can our laser technology is good. We can really focus our lasers to have a small frequency of lights, only a few types of photons. But if we have many types of photons, that's not a big deal. What we could do is we could flip the reaction, the experiment a little bit. Let's say we have, I'm going to put one here. Let's say we have one photon. So this is photon 1, for example. And then we have another photon. Now photon 2 looks like this. Remember, they have different frequencies because, and wavelengths because they have different energies. Now we're going to just blast our sample with 3 particular photons, 1, 2, and 3. Now let's say that we want to know which of these causes A to go from a ground state to an excited state. Well, what we do is we simultaneously blast our matter with all of the photons. And then what we do is we let the photons kind of blast through. And let's say that 1 makes it through and 3 makes it through, but 2 is gone. We have some sort of detector, some sort of computer that's looking at the light coming out. So we shine light on our sample that has a bunch of photons. For simplicity, let's just pick 3. As you might expect, we could have like, you know, just a huge supply of photons of different types, of different energies going into our matter. And we just hook up a computer, and the computer behind the matter that gets excited, it doesn't look at the excited molecule. Instead, it looks at the light that is present at the end of the experiment. So it knows what went in and it looks at what went out and it does like a little subtraction experiment. It says 2 is gone. Well, that's what a lot of absorption spectroscopy is. Once we know that 2 is gone, we know that the excited state for a matter has an energy difference from the ground state. The ground state to excited state has a difference of the energy equivalent to photon 2. Photon 2 was just right. It wasn't too high energy. It wasn't too low energy. It was perfect. I mean, this is great for many reasons, because what we can do is we can look at a lot of different excited state, ground state to excited state transitions in a single experiment. And also in a single experiment, we can use a more practical source of light as opposed to a highly focused laser. In some cases, we could just use a light bulb or like a black light bulb or something like this, something that produces a huge range, a huge spectrum of photons, and we can study all of them simultaneously. So this little subtraction event where the computer reports back, and don't worry about like what detects the photons. That's not complicated technology these days. But if we look at what's gone, just by inspecting what was at the beginning and what is still present at the end, and we report back what's gone, we can get some idea, a lot of ideas about the types of ground state and excited states available to the matter that we're studying. Okay, so that's absorption spectroscopy in a nutshell. It's actually one of these things where you sit there and you look at it in the outset, and you're like, man, this is super complicated. And then you kind of dive into the details a little bit, understanding what technology can do for you these days. And you realize, oh, wow, this is actually fairly tractable and can be, you can see how it can be managed. And just looking at different sources of light, we can look at a lot of different transitions. And we'll get into the NMR ground state to excited state transition next time.